experts from around the country in to see, to tell us what they're doing and to help us learn what's going on around the country. You notice that there's a problem that Minnesota does Minnesota things, Nebraska does Nebraska things. They are not necessarily the same, so we want to bring everybody together as much as possible to share our knowledge. So this seminar is funded through the University of Minnesota Water Resources Center, the Clean Water Legacy Amendment, and the Clean Water Council of Minnesota, and hosted at St. Anthony Falls Laboratory. This month's seminar theme is dynamic design. We'll start with a presentation by our invited speaker, followed by a panel discussion with Minnesota experts for about an hour. It's my honor to introduce this month's invited speaker, Bridget Wadzuk, who is a professor in the Department of Civil and Environmental Engineering at Villanova University. Bridget received a bachelor's degree from Villanova University and master's and PhD degrees from University of Texas at Austin. Her advisor was Ben Hodges. Villanova University, for those of you who don't know, many of you do, is well known as the largest and most effective research center for stormwater treatment and management. They have two effective research centers, the Urban Stormwater Partnership and the Center for Resilient Water Systems. And Bridget has been an essential part of the development of these programs through her research and management. I'd like to give you Bridget Wadzuk.
Thank you. Thank you all for coming this morning. I'm really excited to be here and be speaking as part of this series, but just in general to come and visit you here in Minnesota. We're going to be talking about stormwater green infrastructure today and the work that's been being done here in Minnesota and Minneapolis. I keep wanting to combine those two words together in an awkward portmanteau, and it doesn't go well. But you've done a lot of really wonderful work here in water resources in general, but specifically in stormwater as well. So I'm more excited to get to the discussion portion after hearing your questions and then participating in the panel as well. So the topic that I wanted to talk about today, you know, some of the ideas that I'm going to be showing aren't necessarily, you know, new ideas, but I think we're at this point where, you know, we're kind of grappling with how to sort of move forward. And that's where I kind of came to when I was trying to figure out what a title should be. We're going to be talking about dynamic design, but really it's more than just thinking about design from a dynamic point of view, but really how can we start moving all of stormwater green infrastructure forward. So, you know, I teach at Villanova and I teach a lot of the water resources classes, you know, undergraduate, like fluid mechanics and hydraulics and whatnot. And so whenever we get to, I'm not advancing, sorry, one moment. There we go. So whenever we get to the beginning part of the semester where I talk about Archimedes' principle, I always like telling the story of Eureka to the students. And so as I was going around and thinking about this talk, I stumbled upon this quote, and I kind of liked it as kind of a setting the stage for where we are. So this quote goes, "Eureka can be an answer to a question we have never asked. It can be the articulation of a sudden and unforeseen idea or the expression of a magic moment that throws us into a new world." And I don't think that we haven't asked the questions. And I don't think that where we are has been kind of bumbling along, not unforeseen. We've definitely been moving along a trajectory, but I do think we are at a magic moment. And so I think that is our Eureka moment. And I think what this magic moment is right now is we now have, between the work that we've been doing at Villanova, the work that's being done here at Minnesota and at other places across the country, we now have a couple decades worth of knowledge on how these green infrastructure systems are working, the hydrologic processes that go into them. And so we have a lot of this knowledge. We also have this point right now where technology is really becoming much, much more accessible in terms of our sensing and then our data analysis. Data science itself is coming into its own and really being applied in many, many different areas. And then we also have this kind of social component where there's a lot of attention being put onto stormwater, and not necessarily just the large flooding events, but even these everyday small frequent events that are a nuisance, right? They cause those minor flooding and just, some of that traffic that we're dealing with. So we have, I think, this nice confluence of events that is really going to let us kind of step forward and make one large step forward, I think, as opposed to incremental changes in the very near future. The other side of when we make a big step forward and not just an incremental change is when there's some sort of tension. And we can talk about there's probably a few different areas of tension within current stormwater design, but I'm going to focus in on one today that I think is there and where dynamic design could potentially be a solution. So the first is that we need systems that are flexible and adaptable to be able to uniquely respond to their immediate environment, right? There's a lot of heterogeneities in all of the places that we're putting these different green infrastructures, especially when we're working in urban environments. I am working with PennDOT and AECOM on the Interstate 95 corridor, and we have a rain garden that we're working on there where the infrastructure underneath the rain garden is this wonderful cross-section of Philadelphia infrastructure, has these old masonry walls from who knows, maybe Ben Franklin's time, some nice like mid-century pipes, and now we're putting a rain garden over top of it. And that's a very unique site, and that rain garden has to figure out how to be built and designed and work in that area where we're never going to see something exactly like that again. So we need these systems to be flexible, but at the same time, every time we need to make a custom site, it's expensive, right? It takes time, it takes money. So the other side of the coin is we need a system that is a little bit more standardized so we can enable more efficient and economic design, construction, and operation and maintenance. Borrowing a little bit more from kind of the capitalist side and, productive product development is, can we take one widget and have it apply to different applications? Or can we take widget 1 and widget 2 and put it into make this machine, and widget 2 and widget 3 and make this machine? So is there a way that in green infrastructure, we can start thinking about how we can kind of standardize some of these designs and put them together in smart ways to get more economy of scale? So these two things are a little bit in tension. I think this is where maybe dynamic design can at least be part of the solution. So this is a little bit of a tension, but the other aspect of this is we still need to, I think, define the context a little bit of green infrastructure. I think in the early days when we started moving towards stormwater green infrastructure, we were really trying to sell it to people as an idea. So we're like, it can do stormwater and it can provide a suite of ancillary benefits, right? It's going to clean your air. It's going to have social benefits. It's going to have environmental benefits. It's going to have aesthetic benefits. And now we want these little green infrastructures to do so very much. And so sometimes I think we get a little bit confused in terms of design. So we often will say that stormwater green infrastructure is supposed to be for these everyday, small, frequent rainfall events, but yet then we design them under extreme rainfall conditions, right? And is that really the appropriate context? So we still kind of have to answer this question as well. That's a step back from dynamic design. Can't answer that question, but it can be a part of the way we think about the role of green infrastructure. So just getting into, of course, these, again, nothing groundbreaking here, but setting the stage. So traditional green infrastructure design, it's typically using a volume-based approach where, depending on where you are, you may have slightly different ways to do this. Typically, we either take ponded storage and your subsurface void storage. That's the space you have available to hold your storm, or your ponded storage that has to infiltrate with some time, usually ranging anywhere between 24 and 96 hours. I think here in Minnesota, it's 48. In Pennsylvania, it's 72, right? So we just basically treat these things like a bathtub. So we try to do the volume component, usually capturing 1 or 1.5 inches immediately, right? Just all the water coming in all at once. But then we also think about how these are going to handle peak flow rate. And so we want to manage typically those smaller, more frequent events like the one-year storm. But then we also want to do sometimes peak rate matching for lower frequency events as well. And often we're going to apply the NOAA, one of the NOAA distributions, or like an NRCS type 2 or whatever distribution. And, I'm not sure how many of you saw Bill Hunt's talk last month, but there was a lot of discussion on, for extreme events, is NOAA Atlas 14 really the best way to be, the best tool to be moving forward with a large flood infrastructure design? And I think we can have the same argument when we're talking about green infrastructure design, is should we be using these kind of extreme distributions that we have associated with the NOAA Atlas? And then sometimes we add in water quality loading as well to what our design goals are traditionally. So all of this comes to, this is how we've been kind of thinking about and designing these systems over time. And what I'm going to show you is a series of systems that I call overperforming. And I think this is also something that we need to think about and kind of come to some terms with. And I was having some conversations this morning in terms of what is overperformance. So here I'm saying as a system that regularly exceeds the design expectations, the static design expectations, so that volume-based approach, right? But what do we consider overperformance or exceeding those expectations? What do we consider underperformance? I think is actually something that isn't a clear definition quite yet. But all of these sites I'm going to show I consider to be overperforming. And this isn't, I'm not cherry picking just the good ones. These are, we consistently see, as long as a system doesn't fail pretty immediately after construction, usually due to some sort of construction issue, whether there was compaction during construction or maybe it just wasn't designed quite right, and that caused a pretty immediate failure, typically these systems seem to persist over time. So this is a site on Villanova's campus. It's a rain garden that we've been studying since 2003. And with that, we've seen over 1,000 rainfall events, and we've only seen 26 substantial overflows. Yes, some of those overflows did occur for rainfall less than the design. However, there's many more events where we had rainfall greater than the design condition and the system fully captured them. So I consider this, in my opinion, an overperformance, right? 26 of 1,000 is a pretty good performance rate, I think. Oops. This is a newer rain garden system near the Philadelphia Zoo that we've been studying. And same story, less amount of data that we have, but again, what we're seeing is it's well before or well beyond what our design rainfall was until we start getting overflow. And again, even under some large events such as this one here, we're still able to fully capture it. Then we take ultra-urban settings. So this is nearly a 100% impervious watershed area. And what we see here, this is an infiltration basin with some tree pits all along the street here. This site that we've been studying, we've never seen it fill to capacity. We actually did we tried to force it. We put in a bunch of water to try to break it, and we couldn't. So it's just infiltrating a massive amount of water. And then here's another tree trench system in Philadelphia. And again, similar story here. Yes, we've had a couple of excursions where we saw overflow, again, above the design amount, and again, still design amounts or rainfall amounts that are above the design that are captured. Again, you've seen data like this before, and then, we get into why. Why is that actually happening? So this is the zoo rain garden that I showed you a couple slides ago. And what we wanted to do is try to break it, like figure out how much is it really going to take before it fills up. So the system was designed from that static perspective to capture 36 millimeters. So we've been conducting something called simulated runoff tests, or SRTs. We also find these are a really great way to do right around construction time to see if there is going to be any of that immediate failure. Like, is water getting in where it wasn't supposed to? Is water getting out where it wasn't supposed to? So we've used it actually to construct construction issues or to fix construction issues. But we also use it to kind of test our system. So in this SRT, we wanted to figure out how much water could we apply until the system filled up. So what you see in the black bars up here is this is how we put water in. We started putting water in at 0.2 centimeters per minute, cranked it up to 0.25 centimeters per minute, and then ultimately 0.3 centimeters per minute. So this is a pretty high application rate of how much water is getting into, coming off the street, if you will, coming into the rain garden system. And then we have this blue line. This is the ponded depth in the bowl of the rain garden. And what is interesting, if you look at the rising limb of the ponding depth curve is regardless of how fast water is coming into the system, you see the ponding depth curve rising at a pretty constant rate of around 0.2 centimeters per minute. So even when our fill rate went higher, our ponding depth rate didn't increase. This system is hydraulically connected to a rock bed next to it, and what's happening is water is infiltrating through the system and then into that rock bed. So what we see is that infiltration is happening during the entire event, and then immediately after we shut water off, we see a recession limb right here in our ponding that's on the order of 0.3, 0.4 centimeters. So we see a recession rate that's greater than our inflow rate. So that's why it took a long time for us to get ponding and getting nearly 2.5 times the performance that we designed this for from a static approach. So, again, we've been looking at this over time. And so how can we start taking advantage of the infiltration that we expect to be happening through the event and then immediately after the event? So we know infiltration or exfiltration is happening during the event. We've been studying evapotranspiration, and we know that happens all the time, and that is a big component in helping to restore the capacity of a lot of these green infrastructure systems in that inter-event time, preparing it for the next event. And then we also know that there's a seasonality component, right? So when you saw some of those systems where maybe there was overflow and then for a same size event there wasn't, is there a seasonality component to it? So this gets us to thinking of if green infrastructure is really supposed to really be for managing those small frequent events, then we should try to match the design to match that local hydrology. So that's what we're trying to do here with dynamic design. And a couple of other points that are motivating us. This is some work that a graduate student who worked with me a couple years ago, Dr. Amanda Hess, was working on. She was looking at small rain garden microcosms, we call them lysimeters, and of different soil types. And she was measuring the outflow, or that's your exfiltration, and then the ET. So the outflow or exfiltrations in the dotted lines, the ETs and little symbols. So as expected, right? When it rains, we get a lot of infiltration immediately, and then we see that persist over the next day or two, and then it kind of stables out. Depending on your soil type, you might get a longer period where you still have some sustained infiltration. And ET is happening consistently every day after. And we keep accumulating our ET until we start getting an ET volume that is actually relatively competitive with some of our infiltration volumes. So we want to figure out how we can include the infiltration that's happening, not just during the event, but after the event, and then the exfiltration that's happening, or excuse me, the ET that's happening as well. And that seasonality component, this is data from the Hartranft tree trench, which I showed you previously. Just a few examples here. And again, we know this, the recession rate, how quickly the water that had been ponded in the tree trench starts to recede. We see that there is a seasonal component. It goes faster in the summer, it goes slower in the winter, because we know that temperature is related to the viscosity of water, and how viscous the water is going to say how fast the water can infiltrate into the ground. So again, how can we take advantage of this? And as we were looking at this, we started thinking about what happens in Philadelphia. And we don't have the winters that you all have here, luckily, because I'm a baby when it comes to really cold temperatures. So instead we just kind of, fluctuate around warm, cold winters. And then we have pretty warm summers. And, what is our worst case scenario? If we're thinking of designing for these large hydraulic structures like spillways and flood management, then we do need to be thinking about, your PMP or these really kind of extreme events. But these are green infrastructures. If they fail, water just bumps over the side and gets onto the street. Right? And I don't want to diminish the severity of that, but we have a different scale of what the risk and impact is. So the next thing we did is working with one of my other students, Dr. Carol Albright. We started to look at, well, what's happening in Philadelphia? Like, when do we have most of our rain? And when do we have most of our infiltration in ET? And for us, it's very nice because we get most of our rain. So that's this light blue line. We get most of our rain during the summer months, which is when we have most of our infiltration and evapotranspiration, right? So what she did here, this is a simple model scale She just took a relatively conservative saturated hydraulic conductivity, did a temperature correction to it over the course of the year to get a potential infiltration rate. And then we used Hargreaves, which is temperature dependent potential ET. So that's this kind of darker red line. And then using about 68 years of data from the Philadelphia airport, took the max rainfall on any given day. And that's this lighter blue line that we see on here. So if you think of every day as a mass balance, right? What goes in must come out. So the rain is coming in, and what's going out is your infiltration and your ET. And what we see is we only actually have about 3 excursions where on any given day, historically, the max rainfall would eclipse typically what we would be able to get rid of, the outflow from infiltration and ET. And again, we see a lot of our rainfall is happening when we have these higher temperatures. So this gets us again to that, how can we start to match our design to our hydrology a little bit more? And then one last thing, thinking about our rainfall, is a lot of times with these green infrastructure designs where we're just trying to treat volume, we say, okay, all the volume comes in at once, but that's not true. That's not how it actually works. And when we do try to put a distribution on it, we put a distribution like the NOAA type C that we have on here, or one of your NRCS type curves. And this is a large event. This is not a typical green infrastructure event, but just kind of drives home the point that this is what is a larger, less frequent event, and we still don't see this distribution. So this is 3.76 inches in 24 hours. This is around the 4-year event in the Philadelphia area. And the blue dots on here are the actual rainfall. And so you see what the rainfall normally looks like, right? You have some periods where there's some intensity, and then it goes back down to a little bit more of a drizzle. Then you have a little bit more intensity and kind of goes seesawing back and forth. But rarely do you get this one large peak intensity event that you get out of the NOAA type C distribution. And again, if we're trying to design green infrastructure to handle these everyday events, does it really make sense to design for this extreme case, or should we actually be designing for this case right here, which this case potentially could be more limiting? In this one example, a lot of the rainfall is coming at the end of the event, right? So if we've saturated our system, maybe we actually get more outflow potentially, right? Because of what's happening here. So thinking about what the appropriate rainfall pattern that we should be applying to these systems is. So all of this kind of comes together to get us thinking about dynamic design. And we have 2 approaches that we can use. We can use the design storm approach, which is kind of the classic approach that we're typically using, where we say this is our design storm, and it's like a single event. We make an assumption that the system is empty when we start, and then we apply whatever our design condition is, and then we go on with our design. And we don't necessarily think about when this is happening during the year. We don't think about what is happening within the watershed at all. So it's a pretty isolated case. And then we have continuous simulation. There has been, I know, a lot of work done on continuous simulation. Like I've seen a lot of the work here in Minnesota on continuous simulation and how that has informed a lot of the design and your MIDS calculator and things like that. So how can we kind of move towards a continuous simulation as well and include the appropriate physical parameters within them? So we're going to talk about the design storm approach first. So I don't know all of the details of your MIDS calculator and everything that went into it, but it seems like the continuous simulation that was trying to include some of the infiltration and ET processes is included in there to a degree, what it kind of appears like. This is something that we're piloting in Pennsylvania. So this is just proposed right now, it's not yet approved. Excuse me, but taking what we've been seeing of we do have infiltration during an event. We do have ET that's happening after the event that we want to take credit for because that's what's really preparing the site for the next event. We're coming up with this schematic. And to walk through, what Pennsylvania is requiring is for us to handle the 24-hour event. And we know infiltration is happening during the entire event, but to be conservative, we're going to say, let's take credit for half of that time. So a rainfall comes in over 24 hours and we have 12 hours of that where we say we're filling the media, and then we start allowing 12 hours of infiltration during the rainfall event. Then we take that 12 hours and an additional 72 hours to get rid of our ponded volume, because that's the regulation in Pennsylvania. So we have the additional 72 hours, and then we also have an additional 3 days. And in this time, from the cessation of rainfall to the end of this 7-day period, we're allowing for infiltration and for evapotranspiration as ways to recover our storage capacity. We chose a 7-day period because looking at long-term statistics of rainfall in Pennsylvania, rain happens on average once every 7 days. That's where we got the 7 days from. So not just, oh, a week seems nice. That's where that value came from. And then we needed a way to include evapotranspiration. And again, we're doing this from a design storm approach. So we wanted to keep it simple and not overly complicate how we're putting in, having to run green amps for infiltration or having to run one of our evapotranspiration models. So this is some work continuing that what Dr. Amanda Hess worked on that we're trying to include within the manual, is trying to take all of those studies that we found where we were quantifying how much infiltration there was and how much ET there was, and putting that in terms of a void space credit. Okay? So one of the ways that, again, in Pennsylvania, we're accounting for a design storm approach or a volume-based approach is you can take credit for your void storage space. And typically, it's something like you're using sand, you get 30% void space credit. And like, that's your material, that's your credit, right? So the green line, the top green line on here is sand. Combining the traditional void space and then trying to connect how much water we were actually getting through infiltration and ET, we were able to put this into a volume per volume perspective and look to see what we could get for void space. So if we look at this green line right here, and just worry about the solid lines for right now, this is going to be depth dependent. So for example, if we have 40 centimeters of soil depth or rooting depth, we can actually get almost 38% void space credit. So it's a way for us to take advantage of the void space that ET is going to free up, as well as what's going to be stored and infiltrated. And 38% gets pretty close to 40%, which is your void space credit you get for gravel, right? And so this maybe helps tilt us a little bit in the balance of let's put in a soil-based system that's vegetated versus an underground gravel type system, right? So one that is going to have all those wonderful ancillary benefits that we actually talked about. So this is hopefully using this type of approach is also going to help us get more of these vegetated systems that we're trying to promote. And looking at this, so this is right here, just, across the state, the points are the traditional static storage model that we have been using. So just your traditional void space and ponding volume. What we're calling the spreadsheet model is that schematic that I just showed you, 12 hours of infiltration, and then the ET void space. And so the spreadsheet model is the dotted line on here. And I think a nice way to put this is in terms of, we're saying SCM, stormwater control measure, interchangeably with green infrastructure, that the physical footprint of these sites, we can actually, just by taking advantage of that infiltration during the event, even though it's conservative, taking advantage of that ET with that extended period of time, we can pretty substantially reduce the footprint size for, these are type B soils and type C soils. D soils, we don't really see much of a change, but that makes sense because D soils, you're not going to get a ton of infiltration in 72 hours, right? And particularly in the urban environment where space is premium and space is really expensive, being able to reduce your footprint size substantially, this means a lot. So one other thing that we're batting around, this is more working with Philadelphia Water Department, and we're still very much in the conceptual stage here, is the same idea. What is an appropriate rainfall to actually be using, as opposed to the NOAA type C distribution? What is a good KSAT to use in lieu of infiltration, and how can we let that vary over the course of the year? And then what we're suggesting is run your design storm as you have been doing it, but do it iteratively. And by making some adjustments to your rainfall and KSAT, and then kind of keep spinning through the model. Because then what you can do is you can say, well, if I'm designing this for 1 inch, but it seems like it can capture my 1 inch. Well, see what you can capture. And then you can either resize your system, make it smaller to just capture the 1 inch, or you can take more credit, right? Or say you have a lower risk. So these are different ways that we can think about it. So the design, or the representative rainfall, this is a very new idea. This is just a couple days old that we've been playing around with this idea. We're looking at 3 years worth of data, and what we did is we decided to bin our rainfalls. So these are all of the rainfalls at this one site for 3 years that fell between 0.95 and 1.05 inches of rainfall. And we can look at, this is just the distribution over time. So we see this one event, the blue dots, that's a very long 1 inch long event, right, 42 hours. But then on the left-hand side, the green dots, that's a very intense event. But you see all of these other ones in the middle, and some of those lines actually cross over quite a bit. So maybe we actually use one of those lines in the middle. Is that really most representative of the rainfall distribution that we should actually be applying? We're not forcing something like a 1 year, 24 hour. We're not forcing a certain distribution. And you look on here, and most of the events are kind of in the 8 to 12 hour range, right? So it might not be appropriate to design over a 24-hour window because that's not the way we're seeing rainfall, right, for what our design condition is. So we're still playing around with what the answer is going to be, but this is kind of where we're headed with choosing a representative rainfall. And then we've also been looking at data to try to figure out what would be an appropriate way to try to modify your infiltration over time. And what we did is we looked at a bunch of data and calibrated a bunch of different sites, and we came up with these multipliers to apply to your KSAT to get the infiltration. And what we're suggesting for the Philadelphia area is a multiplier of 1.6, which puts us at a season of May, which when we think about it, that kind of makes sense. May, well, Philadelphia did not get the memo that it was supposed to be warm last week, but typically May is getting warmer. And we do have a lot of rain, right? But we don't have these big extreme events. We have rain probably more frequently than those once every 7 days. You know, last week we had rain every day. But typically we probably in May get rain more like every 3 to 4 days. Not really big events, but is the system ever fully recovering? So by the end of May, that's actually really stressing these green infrastructures. So maybe May is like an appropriate month to kind of design for. So we're suggesting if you're doing a field test, whatever month of the year that you do your field test, you adjust your KSAT to be that KSAT of May, and then applying a rainfall pattern that we think is appropriate. So we're also going to take, so this is all for that design storm approach, but we also like to promote continuous simulation. So we're going to take the same concept here and move it towards continuous simulation. So our KSAT goes both ways. But then for the representative rainfall, we can either choose a representative year. That's what Philadelphia Water Department does, Alexandria, Virginia does it, and a couple of other years. One of, again, my former grad students, Dr. Carol Albright, she was doing statistics on different years and was very unsatisfied with the way the statistics were coming out of looking at rainfall data, trying to come up with what is the most representative year of rainfall data. And so she gave up on statistics and said, I'm an engineer, let me do calculus. Like, go for it, go do calculus. And so she came up with this calculus-based distance approach. And the solid lines on here, we came up with 5 what we consider the most representative years. So some of them have, you know, tropical storms or hurricanes that come through, some have longer periods of drought, but we kind of all end up with a signature that is pretty typical of the Philadelphia area. Her technique was also able for us to identify outliers. So the black and green line are 2011 and 2013. Those are our extreme wet years. And then 1992, the red line, is our extreme dry year. And so what we think, or one way to suggest, is moving forward, you can now start to create your own rainfall record out of this. So you can create 3 wet years in a row, 3 representative years in a row, mix it up, put a couple of dry years in there, so you can start to create maybe a representative decade, a representative 20-year period, if you want to go through continuous simulation. Excuse me. And then lastly, we can just use our long-term historical data record. For the Pennsylvania, we're suggesting a minimum of 20 years. When you do a lot of climate forcing, They suggest a minimum of 30 years. The nice thing about using historical record is, if you have it available, is it is the rainfall that actually happened. But I think maybe we should actually move towards using a climate forcing and doing continuous simulation with a climate forced rainfall record, because we are designing for the future and not the past. So looking at a continuous simulation versus the design storm on here is that Pennsylvania design storm with the 12 hours of infiltration and the ET void space. And again, here's our soil group. Continuous simulation and that design storm approach, really no difference in our footprint size when we're looking at A and B soils. But as we get in not so great C soils and D soils, we actually see continuous simulation shows improvement in, or meaning a decrease in footprint size, because the restraint that's been taken off is that 72 hours of ponding time. Because if it's continuous simulation, it just needs to be ready for the next storm, which might be more than 72 hours, right? So what this allows us to do is maybe put green infrastructure in places that we didn't think previously we were able to do it. Just another couple of comparisons of observations, continuous simulation, and that static volume design. This is the Villanova University rain garden. So the bar on the left is observed. These two are continuous simulation using dynamic design in two different ways. And this is the static. And what we see here is that the static design is always showing us more number of overflows annually than our continuous simulation dynamic design models and what we actually observe. But you see the continuous simulation dynamic design and the observed are pretty close. So the difference isn't super distinct here, but it is here with the heart tree trench, right? The static design is often quite a bit larger, sometimes double the amount of number of overflows. And the key piece that's different here is the rain garden is basically a big bowl. So your treatment area is mostly the bottom of the rain garden, which is most of your area. Whereas in the tree trench, you know, it's a relatively small footprint, but it has those walls. And by using a dynamic design, we're allowing for the exfiltration out of those walls. So a lot bigger surface area that we're able to take advantage of. And again, what you're seeing is dynamic design is matching our observations pretty well. So some of the benefits of dynamic design, as I see them, is we can start also thinking about other things like the geomorphology and flow duration. So we get a better idea of this. This is moving more towards this concept of, you know, a one water approach, where we are considering not just our green infrastructure, but what's coming into our green infrastructure and what's leaving our green infrastructure on a larger watershed basis. We can bring in that water quality component relatively easily. We can move perhaps more towards smaller footprints, making areas available that maybe previously weren't. And that goes along with, you know, maybe encouraging more vegetated systems as well. And then eliminating components that we've put in previously that maybe have a higher failure rate or are harder to maintain. So, you know, when in doubt, it's always been, okay, we want to do this kind of vegetative feature, but just put in a rock bed or put in some gravel storage, because that's going to take the lion's share of the volume. However, those can fail more easily and they're a lot harder to maintain. And I think where we are right now, you know, again, working a lot with Philadelphia Water Department, every time I talk to them, I hear the word maintenance. 20% of the words that come out of their mouth is maintenance, right? It's like maintenance, maintenance, maintenance. And so the maintenance piece is a really big part of it. So if we can eliminate components that need to be maintained, great. And then we can also start getting actually to those ancillary benefits that we talked about. Is if we move to a dynamic approach, we can maybe start to design a little bit more for plant health and not just think strictly from a volume approach itself. Like, we can get the volume, but we can also do these other things. And coming back to that maintenance part right here, excuse me, is if we better are designing for and understanding the different hydrologic processes that are happening in these systems over the course of the year, then we can target our maintenance for those times. You know, we were talking earlier about when you have leaf drop or when you have the seed drop. And we know that those things are happening. What could be also happening in terms of our infiltration rates or where we're going to get clogging into our system. So we maybe can have a little bit more dynamic maintenance as well. So this step forward into our new horizon here, I think we're at a really wonderful opportunity. We have a lot of knowledge, a lot of people working on this. We have a lot of technology available to us. And I think we're all sort of standing on the precipice and like really nervous about making this giant leap forward, but we can do it. We're all together. But we can, I think there's, again, we have the potential to add to areas what we couldn't use before, to add technology to these systems, both in situ and remote sensing has improved quite a bit. And I think we have the data analysis techniques available to us now to really make some smart decision making when it comes to both planning and placement and then operation and maintenance. The idea of can we standardize things and have, you know, widget one be used in multiple applications, I think we're kind of getting at that point as well. So we can start to find some economies of scale in terms of our design, and not just thinking of it from the green infrastructure side, but also economies of scale in terms of, as I call it, the hardware of the systems. So your curb cuts and your inlets, your outlet structures, these are all the things that are actually controlling the flow in and out of the system. And I think those are aspects that could be perhaps better standardized. This, I think, also looking from a dynamic design component plays into adapting to and planning for climate change. And then we can, I think, even use this a little bit as we're trying to come up with our definitions of acceptable risk and, you know, what is failure, right? Which our risk and our failure are things that are still, I don't think, necessarily super well defined. And we all kind of have different definitions of them. We were talking a little bit this morning, and if you're a contractor, failure is a bad word. But if you're a researcher, you're like, sweet, what can I learn? So it's not just that difference, but, you know, if your system misses its target once, is that a failure? If it's performing at 50%, is that a failure? What do we actually consider failure? And that goes along with what do we consider risk? And what risk are we willing to accept? We have those well-defined in many other areas of engineering, but not so much in our stormwater, specifically with green infrastructure. So with that, I rest on the work of a lot of others. Some of my contributors here that I'm thankful for their help. And of course, funding support by a large group of people who have made all of this possible. So with that, thank you very much, and I'll take any questions.
So what sort of questions? Michael. I'm surprised you have a question.
Yeah, I never have questions. Mike Trojan with the Minnesota Pollution Control Agency. In vegetated systems, intuitively, you would think that over time, evapotranspiration and infiltration would increase. Does that factor into your dynamic design? What have you learned? Have you looked at that?
So that's a great question about how infiltration and evapotranspiration are changing over time. And we've definitely observed that in our systems from measurement perspectives. We haven't included that yet into the dynamic design. I think that might be, you know, version 1.1 after we get version 1.0, if you will, out there. I think it might just be a minor modification, but we still need everyone to get on board with this idea of dynamic design. Under just accepting that as a concept before we say, and we think it's going to change, because I think we have a pretty good understanding of the role that infiltration and ET have in these systems. But once you start getting into how does that change over time, there's still a little bit more on the research side uncertainty in there. And, you know, all of these systems we're still designing very conservatively. So that uncertainty, I think, you know, that's one of our hesitations. But I think that's a great thing to kind of include in the future. It also is going to play into a lot of what plant palette you have. And this is one of the things that a couple of colleagues and I have been talking about, and a couple of my grad students we've all been like circling the drain, and I think we're going to start understanding this. And there's been a ton of work done in the ag on macropores, but to better understand macropore, and if we can understand macropore prediction, I think that's going to get into a lot of how we can think about how infiltration is going to change over time, because I think that's where a lot of your changed infiltration in these systems is actually occurring, right? Because we've seen permeability go down, but infiltration rates go up, and I think it's the macropores.
We have one question from the online.
Right. The question is, if we base our design on the historic inter-event period of 7 days, how will climate change trends change this? And how do we account for this change without simply reverting to another historic design storm type of assumption?
Right. Another great question in terms of how we can deal with climate change. So there are as many climate change models as we can all imagine. So some of the more common climate change models, the easier climate change models that are being used now, are really just additive or multiplicative models, where you're taking your historic rainfall event and then just multiplying by 1.1 or adding 0.05 to either temperature or your rainfall amount. So it's not actually changing the frequency in a lot of the climate change models that us here in not the climate science world are comfortable with using. When you get into some other models, they do sort of change the frequency of those events as well. And I'm not as familiar with those, but I think this is, if we start moving towards a dynamic approach, if we're willing to accept the flexibility in our own design as our climate science improves and as those climate change models improve and become more accessible to us, I think that's something we can continually change our modeling approach and our dynamic design approach to incorporate those into the future. One of my graduate students, Dr. Connor Llewellyn, when he came into my room, to my office to talk about what he wanted to do his dissertation on, I was telling a story last night, he was like, risk. And I was like, let's narrow that down. So what he came to is, he did a study where he looked at if we're designing a system to control 1.5 inches now, what does that mean in 25 years? What does that mean in 50 years based on some of this climate change forcing? And he actually just submitted that for publication this morning. So hopefully in a couple months, you can read that publication, but his dissertation is online as well. And that gets into it a little bit more.
Yes.
Hi, Joe Firestein from WSB. I was wondering, going back to the plant palettes, what did you use for like vegetation types to get those different coefficients for your?
So in the study that Amanda did, we had 3 common rain garden plants that are typical of our region, and they were seaside goldenrod, switchgrass, and oakberry, right? So that was the plant palette we had chosen. And she then, based on the numbers that we were looking at, didn't actually try to align them with anything that we see from agriculture, because a lot of the plants that we've looked at, they often tend to be like sugar beet seems to be a popular one. So she didn't do it that way, but she just sort of back calculated the KCs, if you will, if you were using the FAO or ASCE Peppermint. And so those were the ones that she was looking at, and she did track it over the course of the year. And so on that one graph where there was kind of low crop, high crop, mid crop, that was the seasonality that was tied into that.
Hi, Brett Emmons from EOR. We've run into this in terms of like overperformance. One question that came up to mind as you were talking about sort of how things might change over time. Have you come across any testing? We've been requested by some of our communities to work with, and even some communities in Canada, to come up with protocols. So once a green infrastructure or rain garden infiltration trench is completed, before it's accepted by the public entity, do some sort of a test on it to say, yes, it met the performance, no, it didn't. I guess, and sometimes we see something that has higher performance. I guess that's 2 questions. Have you run across that? Has it shown that you're initially having higher performance? And then also, how would you maybe account for this idea that may even increase over time?
Right. So we haven't done anything or made any recommendations officially about this, and I know it's not always feasible, but I do actually think that simulated runoff test is probably the best indicator of construction. And very luckily at Villanova, our facilities group has been a big supporter of everything we've done, and they've allowed us to turn our campus into a living laboratory. And right now we have a 9-acre construction project going on that was a parking lot for years and years. There was fill and all sorts of garbage basically underneath the parking lot. And so they're taking the parking lot out and putting in a mixed use building with some green space, but with a lot of green infrastructure. That site alone, I think is going to handle, I believe it's 2.3 inches of runoff. The local township requirement is 1. So way above and beyond. But there's something on the order of around 12 rain gardens and infiltrating features. And our facilities person heard what we had to say, said, do these SRTs. And she had them do SRTs on every single construction site, because on the site that she didn't, on a previous project, that is a rain garden that looks exceptionally like a wetland. So she realizes the ramifications of it. So I think that's the best way to go about doing it. And I was talking about this a little bit with some people at PWD recently, and we were talking about this idea of what infiltration tests do you have to do, or what permeability tests do you have to do? Can you do an SRT or not? And in the structure that you get permitting through in Philadelphia, there's the design side, but then there is also on that construction side. And so from PWD's perspective, where they're trying to meet their volume control to meet their consent decree requirements, if they get what they need to out of design, and then they find overperformance during construction, like after construction, then they can recredit the system. And so that is something that they're working towards, because it's the owner, if it's a private owner, is going to get bigger reduction on their stormwater fee, or more credit towards their stormwater fee. And then that's more volume control that the city can take advantage of. So it really is a win-win to implement something like that. And I think the SRT does a really great job. And, you know, if you wanted to, if you had the capacity, do it immediately after construction, and then a year later, 6 months later, something like that. Yeah.
We have another online question.
Have you given any thought to how we might be able to incorporate water quality treatment and removal performance into this dynamic design?
Yes, absolutely. I focus a lot more on the water quantity side of things. I come from the fluid mechanics and hydraulic standpoint, so that's my safe space. Also working with Philadelphia Water Department, you know, quantity is such a big issue there. You kind of just get the quality along with it. But in terms of what the state is looking at, there is water quality involved. So it is, you know, using that concept of if you get your volume control, then you're going to get a lot of your mass loading control. So what is proposed for Pennsylvania State is using either of these continuous simulation or the design storm models and taking that volume control that you do get and then applying it either to the National Water Quality Database or the BMP International or International BMP database, wherever you need to get your data from, and using those typical concentrations for the land use that you have or the green infrastructure that you have to figure out your reductions. So I would say the water quality side isn't necessarily as sophisticated right now in terms of the dynamic design, but I think that also, maybe that's not necessarily the 1.1 version, but I think that might be dynamic design 2.0 is where you have a more sophisticated water quality model, because we are learning a lot in terms of phosphorus reduction. I know that's been a big thing here in Minnesota in terms of the phosphorus in the wet ponds, like how do you incorporate things like that? And, you know, some of the, I think there's the opportunity to put more dynamic water quality processes in there.
Thank you, Bridget. I think we're going to take a quick break and transition to our panel discussion, which we'll try to start in about 5 minutes, and we'll have more time for questions then.
Sounds good.
Thank you very much.
Thank you all.
Excellent. Welcome back to the panel portion of the Minnesota Stormwater Seminar Series on dynamic design. I have our panelists here. I'm going to introduce them, and then I'll ask them for their relation to this topic to give a little brief introduction. So first, I want to introduce Mike Trojan, who is a hydrologist for the MPCA, Minnesota Pollution Control Agency, and as I like to call it, the steward for our Minnesota Stormwater Manual. So Mike, what's your relation to this dynamic design topic?
Well, first of all, I'd like to thank Andy and the folks at SAFL for inviting me, although I suspect they were having a hard time finding a fourth person. But to be honest with you, this is the first time I'd actually heard the term, but I'm a soil scientist and a hydrologist by training. And so when I did a little research on it, the topic, I mean, it makes perfect sense. I understand the concepts at it. Being an older person, when I see younger people, I always apologize for my generation. And I think the fundamental issue that we face in the next generation is that of sustainability. And green infrastructure is a part of that. And stormwater is a part of green infrastructure. And so my job is, as the steward of the Stormwater Manual, is to deliver information to people like Mike who actually do real work. And so I need to keep a foot in the research world, and I need to keep a foot in the education world, and so forth and so on. And so my relationship, I think, to this topic is to make sure that we're getting good information on systems that are very complex. They're changing all the time. They are dynamic. And to get that information to the people who are actually the practitioners. And so that's my goal, is to come to, I would have been here today if I had not been on this panel, to listen to people who are at the cutting edge of this topic, and take that information and to deliver it to the practitioners.
Very good. Thanks, Mike. And I forgot to introduce myself. My name is Andy Erickson. I'm a research associate here at St. Anthony Falls. I'd like to introduce our next panelist, which is Professor Bruce Willson. He's in the Department of Biosystems and Bioproducts Engineering here at the University of Minnesota. Bruce, what's your relation to this topic of dynamic design?
Once again, I'd also like to thank the organizing committee to put together this series. It's really a wonderful idea, and it helps to get people together from different backgrounds to talk about issues. My background is I'm a researcher and educator. And so as a researcher, of course, I'm interested in developing techniques to improve the design and operation of our systems that we use to manage water resources. And if you look at the tension that was in Bridget's first slide or second slide between, being flexible and meeting the costs and expense of putting them in, well, I'm probably more on, well, let's make the best design and don't worry quite as much about how cost effective it is. I am confident the engineers out there will tell me if it was cost effective or not. So I tend to be on that side. I'm also an educator, and I think it's very important that we implement or we develop this material in our classroom instruction. Back in 1982, just to give you a little sense of my background, you probably think I was in elementary school, but actually I was at the University of Kentucky, and the state of Kentucky, or the Commonwealth of Kentucky, changed their design for strip miners, where there was a volume-based design that we have now, and then they decided to use some software that I developed when I was at Kentucky. That was 1982. And I taught, because the software was pretty popular, I taught workshops in different states. I taught in Colorado, I went to Alberta, Canada, I taught in Pennsylvania, I taught in Kentucky. And I said, wow, you go to these different states and just look at the audience. Some audience sit there and say, oh my gosh, why do we have to do this different thing? And other audiences like, oh, this is really neat. I want to try something different. And I'm trying to think about why the different states, the culture in the different states was so different. And I think it was partly tied to us at the university setting. If we're aggressive, if we bring in new ideas, if we have enthusiasm for new techniques, the students that leave, that go out and work in the world, also carry that with them. So we carry not only a responsibility, I think, in terms of living material, but also responsibility tied to the cultural acceptance of new ideas.
Very good. Thank you, Bruce. I'll introduce our next panelist, who is Mike Isensee. He is the administrator for the Middle St. Croix Watershed Management Organization and a watershed specialist at the Washington Conservation District. Mike, what's your relation to this topic of dynamic design?
Thank you, Andy, and thank you, Bridget, for that excellent presentation. Although it could have used some more graphs, it's my biased opinion. My relation with this topic really has to do with watershed management. Is organizations in Minnesota are charged with using science-based policy and decision making in order to protect and improve water resources within our boundaries. This also includes a sociological component through stakeholder involvement. And so our real goal is to utilize the science to come up with efficient and effective methods for achieving those goals. Green infrastructure is a major part of that approach. And so when we're talking about dynamic design and we're talking about the science and the data of actually how green infrastructure is performing, that is the direction that we have to go, because we have to follow the data to meet those charges by both our stakeholders and our charge for protecting those water resources.
Very good. Thank you, Mike. And I would give Bridget a chance to give her relation, but she gave us about a 40-minute relation to how she relates to this topic. So with that, I'm going to jump right into some questions for the panel. We'll also ask questions from the audience and from the online audience as well. So my first question is actually for the group here. Dynamic design is not really a new concept in Minnesota, right? We've talked about this in the past, and we've heard a little bit about it already. But what do you think is still kind of maybe the biggest barrier that we've seen in Minnesota that keeps us from moving to that next step?
This may sound strange to some of those of you who know me, but I'm actually going to have an optimistic statement here. I don't really think in terms of barriers. I think we're making progress. I think Dr. Wadzuk alluded to that earlier in her talk too, that I'm relatively new to the stormwater world. I've only been in it for 12 years, but even in that time, I've seen great changes and progress. So I think we're headed in the right direction. We're maybe getting slowed down. The regulatory process is a little bit cumbersome sometimes. And of course, we're always wanting for research dollars and that, but I think we're getting there. And so I think it's really a positive story.
Well, I think there's two components. One is technical and the other is cultural, social issues related with willing to accept change. And I think that if we want to be implemented, we have to show that it's cost effective and works. And so I think those are the major issues, is if we have to make the case that these techniques are better than what we're currently doing because they're different than what we're currently doing. I throw this out as a possible, my experience with what causes change. So I told you it was 1982 when Kentucky changed their design standards. And what implemented that change? Why did that change? Well, they changed the design standard from a volume base to an effluent water quality standard from their mining operations. When that happened, it wasn't just meeting and putting together a design. The engineers now had to worry about whether or not the effluent water quality was sufficient, regardless of what the design was. And that put emphasis on not just following a footprint, but making sure that it works. So I'm not necessarily suggesting that we go that way in Minnesota, but it is an observation that we should think about.
Sure. So, being an outsider looking to see what's happening, again, I think what Minnesota has been doing more towards the optimistic view of it is you have been on the leading edge of a lot of this work. And, just the fact that you would entertain this discussion today, I think kind of speaks volumes about, that there is the readiness and the willingness to be able to move forward with something that looks maybe more like dynamic design, or how to incorporate some more of these concepts into the design, and figuring out ways to make them economical, of course, is a big part of it. But going back to a little bit of what I ended my talk with is kind of coming up with these definitions of risk and what is failure, I think is going to be really helpful in helping us figure out, going back to Bruce's point of what is better, right? And so we use these qualitative terms, but we're quantitative people, and we need to figure out a way to bring in some of that quantification into these terms, like better or improved or more cost effective, things like that, or more efficient. And what does that actually mean? And so that's not necessarily something that's specific to Minnesota. I think that's something that is general to everyone working kind of in this sphere, is we need to get better definitions of those things to help us be able to quantify the things that we actually do need to quantify and say, this is indeed, a better way to go about with this design.
Great, thank you. So I think we're going to turn back to our audience. And if we can, are there questions from the online audience that perhaps we can ask of the panel members?
We have one question that says, since maintenance is a huge concern with these practices, should we design systems trying to minimize maintenance, and to what extent is this possible? Or should there be more of an emphasis on creating systems that can be maintained affordably and reliably?
Yeah, I could take that one. Maintenance is definitely a challenge. So the Middle St. Croix Watershed Management Organization, we currently have 127 practices on the landscape that would be classified as green infrastructure or low impact development. And maintenance is certainly a challenge. And one of the things, reading the 2017 publication on dynamic design earlier this week, that occurred to me regarding maintenance is maintenance is going to have to become more of a substantial component of our infrastructure management. Right now, it's kind of a hit and miss. A lot of our maintenance in the metropolitan area is on a complaint-driven basis. We don't necessarily have a strategic approach for maintaining our BMPs at this point. We have moved to an informal strategic approach in partnership with our other watersheds and communities in Washington County. And I think that if as we tighten up the performance of the practices, we're going to lose our margin of error basically on the landscape. And so we have to formalize those processes and make sure they're consistent. On the other hand, the other piece that I see as promising as dynamic design approach evolves over time is better decision making during repair processes. So as we have bioretention basins or tree trenches or other systems that aren't performing as anticipated, essentially becoming wetlands, our repair approach can include better practices to get those systems operating again, and better decision making on things like planting pallets and soil types and amendments, and where our barriers are for those existing practices not to function currently.
Any other panel members like to weigh in?
There was two parts of the question. One is should we build more maintenance-free systems, and the other one, or should we have a more dynamic maintenance plan? And from my perspective, if it's a relatively low-cost system, then it's very difficult to justify spending more cost for expensive maintenance if it's a relatively low cost. And in those types of systems, well, then you should put more efforts to minimize, do the first one, make them relatively maintenance-free. For the practices that are higher cost, then I like the idea of dynamic maintenance, where you have enough infrastructure invested that you also invested in doing more dynamic maintenance on the relatively large cost systems. So how you approach a problem, I think, depends on how much they cost. So I can't remember, Mike, how many practices you have. A lot of them are low cost practices. It'd be very expensive to develop a very effective maintenance program, perhaps may cost as much as a practice to install themselves. So it's a balance.
Just one more thing on that, agreeing that the answer is kind of yes to both of those things, trying to minimize maintenance, but then be more effective in your maintenance. So one of the things that we are doing is we're looking at sites where we're kind of heavily maintaining the system, and then we're letting other sites kind of go a little bit more on the aesthetic maintenance, in terms of, how much we're weeding the systems and things along those. And so we're going to be seeing the differences there. And like how little maintenance can you actually do on some of these sites. But there are some systems where it is going to be more intensive maintenance, but we can also just be more thoughtful about our actual maintenance. So, just simply like an inlet forebay, If it is the size of a shovel width that your municipality uses, it's going to be a lot easier to maintain than if it is a different size than that. And that's, I mean, that's super, super simple, but yet sometimes we kind of miss it, or we'll be like, oh, let's put pretty cobbles where the sediment forebay is going to be. And those are really hard to maintain. And so you have that, we need to balance the things that we think are cute and aesthetic, and what neighbors would like to see versus what we can actually maintain through them. The other thing is, this again goes back to sort of for these systems to be able to respond to their immediate environment, is knowing or trying to get a sense of what you think is going to be the biggest maintenance issues before you even site and choose your green infrastructure that you're going to implement. So if you know you're in an area where there is a lot of tree canopy, or if you know you're in an area that has, in Philadelphia, we have something sadly called the litter index. So if you know you're in an area that has a high litter index, and maybe even what that litter is comprised of, then you can think a little bit more about the infrastructure, both the type of green infrastructure and then the hardware components that go along with it.
Just real briefly, if I'd add, to the extent possible, it'd be nice to get nature to do some of the maintenance for us too. So I think something that's really on my radar screen is getting a better understanding of the vegetation that we're putting into these systems, and putting good vegetative systems in that are going to repair some of the problems that we're maybe seeing.
Very good. Let's take another question from the audience here.
Probably primarily for Bridget. My name is Dwayne. I'm from the Minnesota Department of Transportation. And it's a complicated question, at least from my point of view, and it has to do with design for pre-ET. So we've got this model that suggests that I'll be at this climax community of pond development, but what if I never get plants to grow, which is very common, because in a 48-hour drawdown, I'm actually in a desert landscape, but I flood it every 3 days. But it still seems to be a desert. So along with those ideas is, does the dynamic system really reflect change over time, which is trash plugging, biomass buildup, so that the thing really is changing? And then the last question for somebody, which would probably still be Bridget, is have you looked at media? So if we add iron enhanced sand filtration systems, the iron seems to be really behaving differently, and perhaps not in a positive way. It might do something for phosphorus, but it may not do something for flow. So we're having this and plant growth. So the questions are dynamic media, dynamic designs that deal with when you don't get ET in a timely manner. It might take 2 years or longer, and so on.
All really great, thoughtful questions. I'll try to do them justice. And, with that kind of pre-ET, because they are ecosystems, we're building ecosystems, and ecosystems take time to develop. And, this could be, if you were building a system where you are maybe perhaps more heavily relying on the ET component of it, and you want that to be a big portion of it, it's you put in more mature plants right off the bat, right? And you maybe put in not just a diverse plant portfolio of types of plants, but ages of plants. And that might help you first, not only maybe get a little bit more of that ET component, but get a little bit more of what Mike was just talking about in terms of having nature kind of help out a little bit with the way the system is going to be performing. Because even though a more mature plant is still going to take a little bit of time to, kind of root and get its roots going, it's going to be a lot quicker than if you just put, a smaller feature in, or even seed the system. So I think that's one way to go about doing it. And if you move towards continuous simulation, so this isn't necessarily going to work as much under that design storm approach, but if you move to a continuous simulation, you can kind of play around with thinking of it from the KSAT multiplier standpoint. You can change your KSAT multiplier over time. And so maybe you put a reduction in your first year or two. So you have, what are your, first 2 years of expected performance, and then how do you plan to ramp that up over time? I think that's a lot to ask from the design storm perspective, but I think it could be something that you need to think of, or that you could do in the continuous simulation. And this just brings up one other thing that I'm thinking of right now. I had briefly mentioned that one of the projects that we're working with PennDOT and AECOM on the Interstate 95 corridor, and that is a 25-year-long project in Philadelphia because they're completely redoing all of the interstate. I I don't know if we're going to be working with them for 25 years, but ultimately their plan is 25 years that they're going to be implementing all of these different green infrastructures along with improving the highway itself. And just some of the observations that we've seen is we're studying rain gardens that are done in terms of the rain garden is finished, but the contributing area is actually still different right now, right? And so we have certain sites that are getting more water than they are designed for, and some that are getting less water than they are designed for because actually construction is not done. So that adds a whole nother layer to kind of the question that you're asking about is where does this green infrastructure fit into your larger construction sequencing? Because we often do just think of these systems as these standalone, like we put the rain garden in, we put our infiltration trench in, boom, but most often they're actually part of a larger construction project, and that construction project might be 6 months, it could be 6 years. And so that I've actually just confused your question almost even more with that, you know, and so I think we need to have a little bit of flexibility in the way we think about these things of what is steady state and how much do we want to design for the kind of ramp up time, and whether that ramp up time is during the construction period or immediately after the construction period.
Let's take another question from the online audience.
This is actually a personal question, but since you are talking about these kind of changes in loading to our systems, would that not be an argument then for not trying to pare down our design to be so efficient so that they can't accommodate unplanned for development in the watershed or something along those lines?
Yeah, that's a really good question. Maybe I'll just kind of take the first swing at that one because I see I have a couple of the same concerns when we think about benefits or detriments of changing our current approach. Some of the on the detriment side, we currently are underestimating the impacts of urban soil compaction during development, and so the question is if we're going to be increasing the credit for our practices, are we also accounting for the deficit that we're missing on the landscape for what we're seeing for contribution from areas that we consider pervious in our modeling? We also, some other components that we know occur out in the field but are difficult to model are poor construction practices. So a lot of the systems that we're showing that are overperforming are actually constructed correctly. That's not always the case in watershed management. And then finally, that lack of consistent operations and maintenance that also occurs. So we've got, while our current system may have a margin of error built into it, we have a lot of components in the contributing watershed that could go wrong. On the flip side of that, though, I see that there's benefits because we know that there are definite benefits for volume and pollutant load reduction for practices like stormwater disconnect, swales without ponding depth in them, or soil restoration, which I think is a really big benefit. And under our current system, with our instantaneous volume, we actually don't have a really good way to credit those systems. So it's just kind of a balance on both sides.
I'll just chime in.
Great, go ahead.
One thing, I think that's a great question in thinking about the development, and you know, it also depends, I think, where this is happening and the requirements on your development. So these problems can't just be solved from whoever your water utility is. It has to be your entire municipality has to be on board with this. And so if there is other development changes that happen after the fact in the watershed, you know, how are those mitigated? But one of the things, you know, we keep talking about the credit that these systems get, but the credit that these systems get, personally, I don't think should be, you did this once and now you're good to go forever. And, you know, especially in some place like Philadelphia that does have a stormwater fee. And if you put in a green infrastructure, you can get a reduction in your stormwater fee. That is something that continually gets reassessed. And so having the ability to sort of reassess along the lines of how is the system really performing is, I think, something that we need to consider. And again, we do this in other infrastructures. We design something for one condition, but then we can continually assess it. Sadly, we're not doing a very good job of fixing it. This is why our ASC report card scores are quite low. The ASC report card would not graduate, right? And but we do have that type of inspection, and theoretically we have the ability to then course correct before technically the design life is over. So I think we can take a more traditional engineering approach to it that way.
Great, thank you. So I'd like to ask kind of a question based a little bit on Bridget's presentation, but also things I've been thinking about related to this. And what I kind of see, we talked about volume, right, as one of our standards. We talked about other parameters, but I'm thinking intensity, right? It's really the balance between rainfall intensity, which turns into runoff intensity, and the infiltration intensity or rate, right? What we can manage. So do we need to change our perspective and not talk about volume so much, but think about intensities? Because I wonder if some of those large storms that were relatively low depths were just a low intensity, slow storm, like you showed with the example. I'd like you all to kind of comment on that and how we might progress in that direction, or if that's kind of a tough challenge to overcome in our thinking and our regulations for that matter.
Well, I think design should be based both on volume and rainfall intensities. I think it's not a or, it's an and. And in terms of your different storm designs that you have, it's certainly a big issue that I've been struggling with is you're going to have the intense storms or you're going to have the non-intense storms. And when you should use what storms, what type of design is not a trivial issue. It's very difficult to make that selection. So I think that the answer is both. We still have to look at rainfall intensities and we still have to look at runoff volume. And I think we need, as an engineering community, to think more about how we set our design standards, how we do our assessment. So the risk factor, what is the consequence of not being successful? If you take the continuous simulation approach, you get multiple outputs. You don't get a single output. You get an output for each of the storms. And then that which output you get from the storms would reflect both the rainfall intensity and the rainfall volume. And you look at some cumulative, some frequency analysis of those results to help you sort out this issue of rainfall volume or depth versus rainfall intensity.
I'm going to take a little different approach to answering that question, maybe. One thing that I always get a chuckle out of is when we talk about infiltration and how it mimics natural hydrology. Well, if we build an infiltration system that's taking 40, 50, 60 feet of water a year, it's not mimicking nature. And so I think if we tried to do a better job of actually mimicking, trying to simulate the natural hydrology of a system, it would address the intensity issue too. So things that Mike mentioned, disconnection, trying to store water up on D soils and use them for stormwater and harvest and irrigation systems, using swales, things like that, trying to build a system that more accurately mimics or simulates our hydrologic systems. I think then we don't have to worry so much about design. I think of design more of as a bigger picture kind of thing as opposed to a specific practice.
So I agree with Dr. Willson and Mike, and I just think that it would be interesting to look at intensities based on our current design approaches. A lot of the work that we're doing is utilizing offline design, and so when the system is full, the water is bypassing, and we really haven't looked closely at which intensities do we exceed our KSAT ability for water to infiltrate into that media? And so at what intensities do we actually lose performance? And then how frequently does that occur?
I agree with all of that. Yes, intensity.
Great. Let's take another question from the audience here.
I'm Doug Klimble. I'm a master's student with Water Resources Science and a researcher at BBE. Based off of some of the last responses, I'm really curious to know what kind of changes might be happening to accommodate for this dynamic design with site assessment and maybe how in situ monitoring can inform maintenance practices or long-term monitoring beforehand can inform the initial design. If anyone has some ideas on. Thanks.
So I've been, I work with a couple of different research projects at the University of Minnesota, and this is one that is also being considered by the Minnesota Department of Transportation and some work that they're doing with Dr. John Gulliver, which is how do we, maybe it's a little bit different, but how do we do a better job of predetermining the infiltration rate of the soils on the site prior to design? So it informs the design. Our current standard of practice is doing soil borings right now, and we've gotten actually better at defining soil borings that are more effective for infiltration design because it does have to deviate from our standard soil borings that we would do for building development. But how do we move that science forward so we have a better idea of what we're going to get when we do our design? And I can't really speak to other types of monitoring on the site, but I do know that that work is moving forward.
I agree. I think the maintenance, especially on relatively large projects, should have sensors that allow you to let them tell you that some maintenance needs to be done as opposed to relying on people going out and doing a spot check. And I think that's a doable technology that in the next 10, 15 years should be easily implementable.
Absolutely. The pre-construction monitoring, I think, is the most difficult piece of this. You know, especially if you're in a redevelopment situation and you have a building or a parking lot in the area you're going to be putting something, then it is hard. We're trying to do some pre-construction monitoring on some of our vegetated sites right now to just even see how does the grassy swale that's next to the highway perform versus the, you know, green infrastructure swale that we are going to be putting in, to getting a sense of that. So, you know, I do think with LiDAR surveying, especially now with like blue LiDAR survey that understands things like ponded water. And so doing better resolution and different type of LiDAR survey, we can even kind of get a sense of just how the watershed is shifting. Of course, that's not an insignificant cost, and that should be something that's done at the city scale. But you know, that is becoming something that's more frequently done and more, we are able to manage the data a little bit more. On the post-construction side, absolutely. Sensors are getting pretty cheap right now. And, you know, this is something that we've been working with ourselves at Villanova, and then we've been working with a company called Opti. And they originally, I think, started out more as trying to do real-time control. So actually making these systems, machines, engineered products where you have gates that open and close and things like that. But what they're really seeing is a lot of the utility of their product is as just a software manager and data management. And so at most of their sites, they have a pressure transducer or some sort of level sensor and a rain gauge. And one of my graduate students right now at one of the sites, the constructed stormwater wetland site that we have on campus, is using artificial neural networks to do prediction of performance. So what he's able to do is he can run a ton of regression artificial neural network models on the wetland system in a very quick period of time and get a very consistent rainfall runoff response that is much easier to put together than a swim model for the entire watershed and the expected output that we have there. So again, we need to have some data to train the model, but what we're able to do is through several events, what he's seen is once he trained the model, it's able to predict what the runoff response is going to be, even though we actually have a gate that opens and closes during the actual event. So it's not even just the natural response. And when he's tried to break the rainfall prediction or try to break the response prediction, saying like our pressure transducer, you know, was up a half a foot, or our rain gauge was off for some reason, or the NOAA Atlas or the NOAA weather report was different, the model recorrects itself to give us the response that we actually did see. So this is getting to that point of where we are in data science is we're at this really, really cool place. I think that we can start relying a little bit more heavily on them. The biggest thing with those is you need data. And so that's why wherever you can put a sensor into a system, put a sensor into your system. And they're pretty cheap. So.
I was glad to hear a couple comments about going out and measuring infiltration rates prior to constructing a practice. I'm a soil scientist by training, and I did my research work on macropore flow. And I know in the manual, we send people to a table and you pick out a number. And we know, or we ask that you do borings and interpret borings. And I know, and I cringe when I do that, because I know that what we should be doing is getting out and sampling a site before we actually construct. And I think that's getting at your question. If we had a better understanding of what was at a site, I think we would build better practices in the first place. And I know Dr. Gulliver has been pushing that, and we're trying to push field testing and better field testing and interpretation too, prior to constructing practices too.
Great, thank you. And I do think, you know, one of the advantages of sensors, we do a lot of inspections during dry weather, right? When it's nice, and we don't actually necessarily observe them during wet weather events to see what actually happens. And that's kind of the power of sensors, and the fact that they're being lower cost these days and more accessible, and being able to build really what you need, I think starts giving us the power to be able to do that. And the more data we have, the better, just like Bridget said. Let's take another question from the online audience.
So since we're talking about how we might be able to decrease the footprint of the BMP practices, some people are wondering if you have an estimate of what magnitude we might be able to decrease the size by accounting for that overperformance.
That's a good question. And kind of, if you remember one of the graphs that I did show, I think it kind of depends on the situation that you have. Like, it's going to be different whether you're in an A, B, C, or D type soil, just to use that simplistically. You know, I think though, you know, on average, plus or minus large standard deviation, you could probably do a reduction of around, I would say safely, 25%. You know, somewhere in that region. Again, I think this is where dynamic design would be important, that you actually do the assessment yourself. But, you know, if you can reduce by that size, then, you know, that does save you a little bit of money, but, you know, not necessarily put you into such a risky category. You know, if you remember from the graph, there were some where it was a pretty substantial difference in stormwater control measure side, on the order of, like, you know, having the system size. And, you know, if you can prove that by your modeling efforts, then I think that should be acceptable. But in general, from a cost perspective, I would say at a 25% reduction in a city, I think, you know, spread over many, many systems, that's a good reduction.
Yeah, I would like to add that from my perspective, I think the jury is still out in Minnesota that our practices are over-designed, and there's a couple of different factors in there. When I look at the research, sizing methodology here, and the credit that we get utilizing standard methods such as MIDS is slightly different. Our design approach for our practices is different than just looking at it, specifically speaking about bioretention. Our engineered media depths are a lot less than what has been constructed in the past. And then one of the dynamics too is, I think, the question about, so first, I think we need to demonstrate locally that this is an issue. From watershed management perspective, I typically see issues where we're underperforming from what we anticipated. But that isn't to say that overperformance doesn't exist, just we haven't seen it in the data yet, and we really have to follow where the data goes. But the other piece I wanted to, the other point I wanted to make was, I forgot. Darn it, I lost my train of thought. That was good too. I'm going to come back to it.
Well, Mike mentioned MIDS, and I think it's important to remember too that MIDS is based on continuous simulation modeling. And so therefore, maybe some of the designs that we're getting, if people are using MIDS, are actually probably more on target than some of the other designs. And maybe that's possibly why we're seeing you're seeing more underperformance.
Yeah, and I've got it back. So and the other component of variability that I see in considering where we would be maybe oversized versus undersized has to do with the wide array of soils that we have in Minnesota. So I think that the answer would be different on the Anoka sand plain versus in Carver County, which is primarily C and D soils.
So maybe that, kind of segues into a question about modeling. So we have MIDS, we have other models, computer models that we use. Bridget talked about a model that they're using for predictions. How are we going to change modeling in Minnesota to maybe adapt? Do we have the right tools right now? Do we need new tools? What do we need to do?
This is an exciting time to be working in water resources. And historically, we had very few data points, and we relied a lot on our understanding of the system, mathematical physics and thermodynamic responsive systems, and we build these complicated models. Now we have potential for gathering lots of data points at lots of locations. This means that we have potential to integrate lots of data with complex understanding how systems work and really improve our understanding and design of systems. So this looks like a golden age if you want to work on models for stormwater and other agricultural systems, because the ability to blend detailed data with our existing complex models is really quite exciting. So I think the neural network kind of approach, I say, wow, I see that as a potential direction that we go. Instead of relying on SWIM and these other complex models, we just gather tons of data, use artificial neural networks to define how the system will respond. I think that's probably a mistake because we also have all these process-based models. We need to integrate all this stuff together. So it's quite exciting from my perspective.
I'm not sure this answers your question, Andy, but I think if we start moving more towards hydrologic type modeling, I go to the boundary waters quite a bit, and I've noticed over the years that nature does a pretty good job when left unaltered at keeping the water clean. And so I think if we can do a better job of simulating natural hydrologic systems, the water quality, I think, is going to take care of itself. And so I think if modeling is going to go anywhere, I would like to see better hydrologic modeling.
I have one more point on this topic, and I apologize if I take too much of my time, but it is, in agricultural watersheds, the way we predict erosion used to be universal soil loss equations. It's just a multiplication of 5 or 6 factors together. The new approaches use Webb, where now in agricultural settings, they are going to simulate 1,000 possible weather scenarios for the given field condition and look at the average response. If we can start doing some of that sort of analysis, become standard for agricultural fields, we should be able to also do that in the urban environment for stormwater.
And I think with the ability, with our increased amount of data we have and the increased computing power that we have, where we can do things like the neural networks and run, thousands of models or run thousands of different scenarios to figure out what your soil loss is going to be, it's actually, I think, going to help us tighten our understanding of the uncertainty in our designs a little bit. And then because we can run all of these different model scenarios, and if they all coalesce to one point, then you have a bit more certainty if you just run 1,000 different scenarios about something. And right now, SWIM is, that's our kind of default tool in, our water resources engineering field for this type of stuff. So SWIM is undergoing a major renovation right now as well. And it'll be interesting to see how that comes out. But I think it's going to offer us the opportunity to integrate some of these newer computing techniques that we have. It's also, I think it is already open source, but it's going to be able to really allow people to just join in and pop in, so we can start bringing people who are computer scientists and hydroscientists that have a lot of that computing power, and whether it's improved hydrology models or different components, and it's going to be a little bit more drag and drop. So moving almost more towards an app-based way to think about modeling, I think that's really going to strengthen SWIM's capabilities moving forward. It's not just going to be, this is the model that you have and you just sort of tweak it. We're going to be able to build the model that we need.
Great, let's take another audience question.
John Gulliver from the University of Minnesota. This is a question for Bridget, and I'd like to hear Mike Trojan's point of view too. In dynamic design, you're developing a protocol for the design of BMPs across the state of Pennsylvania, but it's very site specific in the analysis that you have to do to develop dynamic design. So there's a lot of analysis in the background that you've done, and then you develop these criteria that are fairly simple for people to use. But the rainfall is different in Philadelphia than it is in Pittsburgh. And so maybe you could tell us a little bit about how you manage that.
Right. So, you know, I was showing a lot of examples out of Philadelphia, just that's where we have a lot of our data and what we have access to, in addition to the work that we've done for the state. But we are allowing the, you know, rainfall patterns and whatnot to vary over the state. And I think there does have to be some work done to, you know, maybe figure out what is your representative rainfall going to be in this area of the state versus that area of the state. But that doesn't have to be done every single time by each unique person. That is something where, you know, I think I would put that onto the state's capabilities of coming up with these sort of standard sets of rainfall patterns to use, or standard sets of KSAT multipliers to use for the different locations. And so it's not going to be that each and every time whoever's designing it is going to have to do all of these different components. And I think then if it also is kept with the state, then it can be updated as new data comes in, as maybe the state makes different decisions on how it wants to think about climate change forcing moving forward in the future, and you can kind of like tweak it and just say, here, use this. And that's kind of what we were trying to, again, our week old idea of looking at the bands of rainfall that we were looking at, and that was in Philadelphia, but looking at those bands of rainfall. But what we're thinking is we ultimately come up with a band and one of those storms in there and say, use this. So it's not, again, going to have to be everyone doing all of this analysis all of the time. Because that's in the research world, or that's in the development world, but that's not in your everyday design practice world. So
you will have a multiplier based upon whether you're living in your site is in Philadelphia or in Pittsburgh.
Exactly, yeah. So it is, and I'm not sure right now how everything is going to be segmented out, if it's going to be by county or, you know, some other kind of, you know, like a hydrologic unit code type breakdown of how we would determine that.
Well, the only thing I would add to that is I'm not going to add any technical thing. I think she really did a really good job of explaining that. I think I also have one foot in the regulatory world, and so the question is, well, as a regulatory agency, how are we going to develop the flexibility to allow things like that? And I think I don't have an answer, but I think those are questions we're going to have to deal with. You know, we have a kind of a one-size-fits-all approach now with our permit, and so, you know, can we build flexibility into our regulatory approach to allow for more dynamic crediting systems too?
Great, let's take another online question. None? Any more audience questions here?
I'd be curious, from the MPCA or the Watershed Management Group, is there any thought to Bridget's points about designing more for the smaller storms, having a less stringent requirement on the larger 100-year storms or that type of thing, and focusing on the smaller storms? And sorry, I'm Eric Henry from AECOM.
Well, from the watershed side, we're charged with two primary objectives. One is improve and protect water quality, and the other one is to ensure that we're addressing flood control issues. And so large storm events is really a flood control issue. And I think that that's a charge from state statute. So that we're going to continue managing that until we have some evidence that it's no longer an issue.
I'm not sure. I'd have to think about your question a little bit more, I think, but I think it's probably along the lines of what Mike just said, is that we kind of have a charge and maybe we need to have a better discussion internally about questions like that. And,
I think in terms of like green infrastructure and urban environment, it's more applicable than on a watershed scale.
Let's do another question right here.
Yeah, it was just along the same lines. How do you incorporate like policy to economically support these, more appropriately everyday kind of scale green infrastructures when, as far as current stormwater policy goes, a large stormwater pond would check all the boxes for requirements?
Yeah, so I think especially in the metro, well, it's throughout the state now. Stormwater ponds actually won't check all of the boxes anymore. That used to be the case, but on the statewide NPDES permit now, volume control is part of our suite of requirements that we have to meet for new development in the metropolitan area. Volume control has been part of new development, and in most cases redevelopment as well, because all of our waters are impaired, and we only really have two tools for addressing our impaired waters. One is redevelopment, the other one is voluntary retrofitting of our existing systems. So I think we are at a point now where we have, based on the data that we have efficiency and we have effectiveness. And the question is, how does that evolve into the future as we get more data, evaluate it, and adjust those systems?
And if I'm understanding some of the questions and comments, if we try to drive green infrastructure from just a stormwater approach, I think we're going to miss the boat. I think we need to start working with other folks that are in the green infrastructure world. For example, I'm working with somebody at the agency on a project to try to save some of our mature ash trees. And so there's a stormwater credit, but there's a carbon credit. And so there's other credits. And so I think if we can start working outside of our little boxes sometimes that we work in, and work with other folks that have similar end goals in mind, we might be able to drive some of these things.
So that actually leads well into a question I wanted to ask for Bridget and actually anybody in the panel. Where more can we learn about this? How can we learn from others, maybe not necessarily even in Minnesota, but in other parts of the country or the world where they are maybe doing a better job, or things that we can maybe incorporate in Minnesota to advance what we're doing?
So I think there's a lot of people doing really interesting things, and I don't know if anyone has it solved yet. So it is going to be one of those things where you take a little bit from here and here, and you keep working. Of course, Seattle, Washington, and all of Western Washington has always been on, I think, the leading edge of this, and Western Washington does actually require continuous simulation in terms of their design. So we can learn a lot out of there. Of course, there are different requirements in terms of what they're trying to protect as well. They have these high quality waters that they're trying to protect from ecosystems for different reasons. Portland, Oregon, of course, as well. Kansas City is a big one. And then you even learn about these small places that are doing interesting things. Again, on the dynamic maintenance side, Salinas, California, which is a small little community, which happens to have Esri in its backyard, has some really cool data technology, right? And so it's not that they're necessarily on the leading edge of green infrastructure, but they're on probably the leading edge of the data management side of this. So we really can learn from a lot of different groups internationally. The work being done in New Zealand and Australia is, of course, definitely very impressive. And then you have places like South Africa, which has a wildly different water resources problem. They're running out of water, but they're using some green infrastructure strategies to try to help and solve that problem as well. So, are there lessons learned from them directly applicable? No, but conceptually, I think we can take a lot from them.
Andy, I'll just say my goal is to continue to attend your Stormwater Seminar Series as you continue to bring in outstanding speakers from outstate. It's really a wonderful opportunity for us.
Thanks for that shameless plug. Anyone else?
I think that was a pretty comprehensive list. Thank you.
Great. How about one more question from the audience, and then we'll take our final keys from the panels, if anybody has one.
Hi, Brett Brett Emmons from EOR. Kind of building on some of these other questions, one we've worked with a bit and always tried to understand how to approach is like flood control benefits of green infrastructure. I know for a long time that was they were two different things. You design your traditional system the way you always did, and plus on top of that, let's sow this green infrastructure. I guess we've had several projects where we've actually accomplished a lot with flood control within the green infrastructure. But I'm curious if you've seen examples like that in Pennsylvania, Minnesota. Do you start to see that coming into play? And again, for us, it's a lot of times just mimicking the natural system. So if it's a low runoff system, that's what may match the green infrastructure. So it may not be just limited to 1 inch. It may be something bigger.
I think, again, this goes to that idea of, uncertainty and variability, where we've certainly seen a lot of these green infrastructure sites be able to work well under, more extreme events that are more traditional flood control management applies to. For instance, one of the sites that we have on campus, it's designed to hold 1 inch from a static volume approach. When Superstorm Sandy came through the area, which was about 4.3 inches of rain at Villanova in around 36 hours, the system actually only overflowed for about 5 of those hours. And so we actually ended up capturing about 95% of the event. So you look and you say, oh, well, we can use this for flood control management. But we have one of those events come through, in the lifetime of that site so far. And, how much do we want to rest, flood control management? And this is, again, getting to the idea of risk and scale, because with, traditional flood control, lives are truly at stake in terms of the risk. And again, if this treatment train is to overflow, then the grass next to it gets soggy, right? And so those are much different scales of failure. So I think if we want to start putting green infrastructure into flood control plans, I think this is where we need to have good testing to make sure they're actually working as we want them to, and almost retroactively add them into our larger flood management plans, and then ensure that they're being maintained as they properly would be. If we, I think, heavily rely on them just from a design standpoint, I think they have the capability to substantially help flood control, larger flood control, but I wouldn't want to see sacrificed a larger infrastructure that is undersized that, where we're still rather uncertain with the performance of these sites at that large scale.
Yeah, and I think in Minnesota, we can learn a lot from the Inver Grove Heights Northwest area projects that area is landlocked. And so there's a lot of work done with green infrastructure to approach both flood control, but also, or water quality, but as well as flood control for that entire area. And that's just about built out now. It's been about a 15-year process, and I can't remember the exact area, but it's very large. And I think that's monitoring and performance of that entire system would be helpful for helping move the science forward for how we do that, how we do flood control with green infrastructure. So we do have some good examples out there that we could start working on.
Well, great. At this time, what I'd like to do is go for each panelist and let them have a chance to kind of summarize maybe a few key points, but most importantly, maybe some takeaways. What can we take from this, either to change what we're doing or even just consider? How do we consider what we're doing and how we can improve it? So I'm going to start on this end with Bridget to summarize and finish us out. Thank you.
Okay. So again, I've really enjoyed this panel discussion and all of the questions that you've had. And I think we just need to pushing the boundaries. And again, as I kind of started, my talk, where we're at this really interesting point where we have a lot of knowledge and we have a lot of data, and we have the attention and we have the capability to manipulate this data. And so it's more of how do we move forward from here, is really trying to use the data that we have in the most effective way that we can. because that's going to inform this concept of dynamic design, but it's also going to inform everything else we do, whether it's the flood control that we have, whether it's our modeling tools that we have available to us, whether they be rainfall runoff response models or more intensive hydrology models. I think it's really a call to us to work kind of again across different disciplines and bring in people who are in that hydroinformatics world. And how do we take what we know from modeling that we've done in other types of water and bring it into the stormwater? And how do we take what we know from other large scale data management systems and bring that into stormwater? How do we take app development and bring that into stormwater, and integrating, with, if you will, your citizen scientists? So it's, dynamic design, I think, is one example of how we've started to integrate that data a little bit together, more together in a way where it is kind of bringing in these different components. So I think that's an example of it. But in general, it's, we're at this point where we need to kind of get out of our own box here and start working with, different people, scientists, social scientists, policymakers, to figure out the best way to move this forward.
Yeah, I agree fully. Data is on the rise. Our ability to gather data, consolidate it, evaluate it, and adjust our systems based on that data is at an all-time high in low-impact development and green infrastructure. And ultimately, where the data goes is where we'll go with the systems. And we basically at this point need to maintain our efficiency and effectiveness of design, and then as we evolve, also account for the areas of uncertainty that we have now. And again, it's all about the data.
Well, I enjoyed Bridget's presentation, and I enjoyed being a member of the panel. I think there's no shortage. We have many tools that are available to assist us in moving forward with improving our design, improving dynamic designs. I think it's important that we maintain a dialogue between the practitioners, the state and local agencies, and the university researchers and educators, so that we communicate and move forward in the proper steps.
Again, I'd like to thank Andy and the folks at SAFL and the great presentation, great questions and discussion. For me, I think the take-home message today is, again, to kind of get me back on track from a perspective standpoint. It needs to happen every once in a while. As the steward of the stormwater manual, as Andy calls it, I feel like I sometimes get pulled in 20 different directions on very specific issues: bioretention design, maintenance of permeable pavement, this and this and this. But I think at the end of the day, these are very complex systems, and I kind of need to keep in the back of my head that it is an environmental system, and we have to have a systems approach to it. And so it's good to come to things like this and kind of keep that perspective, make sure that everything gets tied in together.
Very good. Well, I would like to thank our panelists and our invited speaker. If we can give them a round of applause.